Alright, so now we're going to do lesson 8.3. I want to remind you guys that you can message me at any time and I can explain something further if need be. Don't feel, like you can't do that. I realize that this is kind of an unconventional learning style, so I want to make sure that you guys are getting the best out of it. So, trig integrals. In order to do trig integrals, you really need to understand your trig derivatives, and I've been pressing that since the beginning of when we started that. So I'm going to write a reminder, probably pretty often throughout the lesson, that the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tan is secant squared, the derivative of secant is secant tan, the derivative of cosecant is negative cosecant cotan, and the derivative of cotan is negative cosecant squared. You have to know these in order to understand trig integrals, because everything that we're doing today is going to be having u sub and having the appropriate du to solve the integral. Alright, so trig integrals are of the form, for example, sine squared x cosine x, or sine cubed x cosine x, or sine to the 7th cosine x. These are all examples of the same type of integral. In each one of these, I can treat the inside function of the composite function as u, and cosine would be the derivative of sine, right? So in each of these, u would be sine, and du would be cosine x dx. So I could replace this and make it u squared du, or make this u cubed du, or make this, well, you guessed it, u to the 7th du. Now some of these are pretty obvious. If you have one that's a composite function and the other one is not, chances are the one that's composite is going to be your u. Well, what we're going to learn today is that it might not be exactly your u, but you might have to do some manipulations to get it to be the appropriate u du setup. So a couple things to remember. Again, we just did this on the previous screen, so maybe we want to do it out a little bit more clearly. We need to know what you need for a valid u sub. So if u, and I say u, this says sine of u, it probably should have said sine of x all the way through, and in my future lessons I'll probably change that to x's. But if your u is sine, then what would you need for your du? Well, you would need a cosine x dx. So actually, let's change all of these to x's. If I had cosine, in order to integrate, I would need a negative sine x dx. To integrate tan, I would need a secant squared. To integrate secant, I would need a secant tan. To integrate cosecant, I would need a negative cosecant cotan. And to integrate cotan, I would need a negative cosecant squared. Now I know I went through that fairly quickly, but I need you to realize that if you have sine, then sine will be your u if you have a cosine to spare. Cosine will be your u if you have a sine to spare. I say sine, not negative, because we can manipulate the negative on our own. Tan will be your u if you can spare a secant squared and all you have left is a tan. So again, we're going to go through that process and you'll see some examples play out here shortly. So here's some rules to look for. If by chance you have sine and cosine, okay, and sine has an exponent of 2k plus 1. Alright, so let's pause here for a second. 2k plus 1 is an odd number. Right? 2k would have to be even. You add 1 to it, you get an odd number. So what this is telling us is that we can take our odd number of signs, save 1, and then the remaining are even. If I save 1, I have an even number of signs. Now, if you take the 1 off, you might recognize this better as sine to the 2kx, And what they did instead was split it up. Okay, I can treat this as sine squared x and bring the k out. Now, why would that be significant? Well, you can take sine squared x and replace it with 1 minus cosine squared x. Remember that identity? If I put 1 minus cosine squared x inside the parentheses, raise it to the power, have another cosine to the power, then I only have a product of cosines, and I have the appropriate du that I needed all along. Okay, let that sink in as we look at the next one. If I have an odd number of cosines, save one of them, the remainder will be even, and I can convert the even number of cosines, 1 minus sine squared x, and then raise that to the k power. Then everything that's not the du can be manipulated to be a product or a list of sines. No more cosines involved. Okay, well that works if you have odd exponents. But what happens if they're both even? If they're both even, then what we're going to do is use some identities to manipulate them a little bit, and hopefully that will change it to something that would fit more into one of these categories. So this is where we're going to focus our attention. If they're both even and non-negative, then we'll try something to get them to fall into these categories, okay? All right, so let's see this. The question you need to ask yourself is, which one of these is odd? Well, that's clear. Cosine to the 5 is odd. The rule of thumb is to take the odd exponent and split it so that one of them is saved for your du. Okay, so cosine to the 4th and cosine together make cosine to the 5th. All I did was split it up into a product. I put a box around this to remind myself not to do anything to it. It's already ready to go. Now, the even number has to be equivalent to a cosine squared raised to a power. In this case, it's 2. Hopefully you remember what I said about the even number of the cosines. Now, if I'm saving a cosine, then my intention is to make all of this sine. This is already sine, so I need to convert this to sine. And I do so by replacing cosine squared x with its identity. If you're not sure where this came from, this is from the Pythagorean identity that says sine squared x plus cosine squared x equals 1. Okay. Alright, so I replaced cosine squared x with 1 minus sine, and you're going to see it kind of unfold, at least what our intentions are going to be here. You will have to do some algebra. It's nothing too terrible. Alright, everything here is a form of sine. I do want it to look as nicely as possible. So I'm going to expand this and get it to be, I say polynomial, but what do I get when I have 1 minus sine squared x times itself? Well, that's going to give me 1 minus a double sine squared x. And then when I multiply these together, I get a positive sine to the 4th. Alright, so this portion right here can now be replaced with what I just expanded it to be. Can you see where we're going with this? I can now distribute this into these into this quantity because it's not raised to a power any longer. I get sine to the 4th x minus 2 sine to the 6th x plus sine to the 8th x. And I'm going to put parentheses around this because they all are applied to this cosine dx. Now I want you to imagine 3 separate integrals. I'll show it this time, but I'm not going to make a habit of showing it every time. The first integral is sine to the 4th x with the cosine x dx. The second integral, and I can bring this minus 2 coefficient out, is sine to the 6th x cosine dx. And then the last one is the integral of sine to the 8th x cosine x dx. And I want you to imagine, now that we have a sine-powered function next to the cosine that we reserved, each one of these is a u sub, where u is sine and du is cosine x dx. Alright, so all of them, sine is your u, and cosine x dx is your du. Keeping that in mind, I don't have to do a lot of thought at this point. I don't need to rewrite it if I don't want. This says u to the 4th du. It says minus 2 u to the 6th du. It says u to the 8th du. So I'm just going to answer the question with the limited space that I have left. And the final answer is going to be, well, what's the integral of u to the 4th? But rather u to the 5th, remember u is sine, over 5. U to the 6th becomes u to the 7th over 7. U to the 8th becomes u to the 9th over 9. And of course I have to remember my plus c. Okay, that's your first trig integral. And of course, you could, if you wanted to double check your work, you could graph this and then graph this to see if they'd look the same. You could give it some bounds and see if it comes out to be the same. There's a couple things that you could do, but of course that plus c might throw us off a little bit. But that is in fact the answer. Alright, so down below, let's take a quick guess as to what u is and what du is. Clearly there's not enough room to solve them, so we're just going to assign u and du. What's going to be my u when sine is odd? In this case it's going to be cosine. Du is going to be negative sine x dx. So to rewrite this integral, just to get it started, I would have sine squared x to the what power? If I'm reserving one of these for my du, then I have 6 left over, which would be 2 times 3. Oops, not cosine x there. And because in order to have cosine as your u, I would need a negative attached to my sine. I'm going to say it with a negative outside. There's more work to do, but that's the beginning stages of this question. Take a moment, pause the video, see if you can find the correct u's and du's for each of these. Now fill in my blanks. Cosine is odd, so I already know that sine is going to be my u. Cosine is going to be my du. And I'm going to rewrite this as sine to the 6x. Reserve one of these, leaving 4, which is 2 times 2. And it's ready to be simplified further. This would get replaced, and we'd square it like we did before, do the 6 here. It would virtually look the same as this, except it would be a 6, and then an 8, and then a 10. Alright, what happens when they're both odd? Well, in this case, you can't lose. You could be either one. My personal recommendation would be to let the smaller exponent be the one that you split, because then if I reserve one of these signs, I only have sine squared, so that's just a quick substitution, whereas if I reserve one of these, I have cosine to the fourth, which means I would have to substitute with the Pythagorean identity, and then I'd have to square it, so there's more algebra involved. Alright, so u would be my cosine x, du would be my negative sine x dx, and the way this would kind of pan out, I have a sine squared left over, cosine to the fifth left over. I save a sine x dx, and I would need to include a negative in both the beginning and the end. Of course, I put a box around it so it looks like the negative is in fact a negative, but you probably should include some parentheses just to identify that that's not a subtraction problem. And then again, what do you do when they're both positive? Okay, what do you do? Well, we have to come up with some sort of strategy, some sort of identity to plug in for each of these to figure it out. Now we know the Pythagorean identity that was written before. Certainly we could try that again. Just a quick glance. I want to make sure I give you the right information here. Of course, I don't have the identities right in front of me, so that was poor judgment on my part. There are some identities, I think they're in the front of your book, so I'm going to try and give you the page number here. Okay. Power reducing formulas. If you go to the front of your book, on the perforated form at the very beginning, it's on the back side, and it says power reducing formulas. And I would take that just for exactly what it sounds like. Power reducing would allow us to get these exponents down, power reducing, and hopefully be something that we can actually work around. So again, I'm going to start with the smaller one because it might get me down to an appropriate number faster. The sine squared formula, and I can write these on another page so you have them. The sine squared formula is 1 minus cosine of 2 times x. So if this was already 2x, then this would become 4x. You see that? Whatever this is doubled. Divided by 2. Now before I continue, I want to pause here and I want to write down what that formula says. It says it says sine squared x can be put into a power reducing formula by replacing it with 1 minus cosine 2x over 2. That's sine squared. Since this is sine to the fourth, then I have to square this, double that. Alright, let's play this out a little bit and see what happens. 2 in the denominator squared would be a 1/4. So for just ease of calculation, I'm going to bring the 1/4 out. 1 minus cosine 2x squared would be 1 minus double the cosine, okay, plus this squared. Okay. Simplify it a little bit. And what I would do at this point, since this no longer had an exponent, a larger exponent on it, I would save one of these cosines, cosine's not the du. So I would distribute, maybe? This is hard to say because there's not a lot of room left. I do want to give you some guidance based on what the question, a similar question, is doing. They went through and then they were able to integrate as is. So if you look actually further, cosine squared can also be in one of these situations. I'm going to cross this out for a second and I'm going to draw your attention to the back where there's a little bit more room. And I want to actually show this through. You had sine to the fourth x and cosine to the sixth x. I'm actually going to use the formula on both of them. Sine squared, just as a reminder from the front cover, is 1 minus cosine 2x over 2. And cosine 2x is the same formula except with a plus sign. And I've told you before, there's a lot of times that I don't go back through my notes before because I want to do trial and error with you. I don't want to give you the lesson and assume that everything is all done out. I want you to actually see the struggle so that it encourages you, hopefully, to power through the struggle yourself. So again, sine squared and fourth, that would be this quantity squared. And then this quantity cubed, right? Squared to the sixth would become cubed. Again, this may or may not pan out as is, but I do want to try it out and see what happens. I've got 1/4 for my coefficient here. I've got 1/8 here, so I'm going to bring them both out front as 1/32. You might be thinking, what did you just do? A square around an entire quantity means that it's both the top and the bottom square. This is different than multiplication, but when you square the entire fraction, the numerator and the denominator both get squared. So now I have a 2 squared and a 2 cubed, both in my denominator. 4, 8 in the denominator makes 32. Okay, so has this helped us at all? Well, again, I'm just going to power through and see what happens. I would not assign this on a test, by the way. We know that this is going to be minus double plus. I know that I'm going to get this again. Actually, now it's plus though, so I'm going to treat this as a 2 and a 1, and you'll see what I mean here in a minute. Okay, here I squared it and then I have 1 left over. Okay, there's a lot of distribution and stuff that's about to happen. Oh my goodness. This may not be the most efficient way, but that's okay. I'm going to do 1 times 1, 1 times that, 1 times that. I'm going to go through with minus 2, or minus 2 cosine 2x, and I get minus 4 cosine squared 2x, and I get minus 2 cosine cubed 2x. Distribute cosine squared. And then outside all of that, I have one more distribution to do. Before I do that, though, I'm going to see if there's anything that repeats so I can simplify this a little bit. I only have 1. Do I have cosine 2x? Yep, right there. The positive and the negative cancel. So I have cosine squared right here. Cosine squared minus 4 would be negative 3. Another one here, which would make that now negative 2. Okay, go on to the cubes. I have a negative 2, a positive 2, and then cosine to the 4th. One more distribution. I get 1 plus cosine 2x minus 2 cosine squared 2x plus cosine cubed 2x plus cosine to the 4th 2x plus cosine to the 5th 2x. I don't see anything that's repeating here. Okay? In fact, it's interesting how it all came out in the same order. Alright, so what can we do? I'm going to be honest. I'm thinking that I didn't do the right thing. So what I'm going to do is I'm going to research this one and star it, and I'm going to come back to you with the right answer. Okay? So I apologize for that, but at least it's a trial. Anyway, we're hoping that we're not going to have evens and evens. And by the way, I certainly welcome your suggestions on what to do there. I will not let you down. I will go back and research that and come back probably with tomorrow's lesson. Alright, so here's a situation. I'm going to rewrite it in the appropriate fashion. You have a 3, you have a negative 1/2. What's the rule of thumb? Take a 3, save, or take the odd exponent and save it. What do you do with what's remaining? Convert it. So if that's my du, this has to be the u that I'm using, so that has to change to 1 minus sine squared. It does not have an exponent on its parentheses, so I can distribute the remaining sine. Oops, I didn't mean to do that. I miss having to write it. Alright, now I've got sine to the negative 1/2 x minus sine, well, 2 minus 1/2 in fraction form, that's 4 over 2 minus 1 over 2, which would be 3 over 2. Both of these, this combination, both of these are receiving the cosine, so I'm going to put them in parentheses, and I'm going to imagine u sub off the top of my head, but I'm not going to actually convert it to u. This is the appropriate du. Integrating sine to the 1/2 would become, negative 1/2 would become positive 1/2 over 1/2. Remember, when I make the fraction in the denominator's denominator comes up as a coefficient. Sine to the one more than this would be 5 halves over 5 halves. And I'm going to plug in pi over 3 minus the pi over 6. For calculation purposes, pi over 3, well, I'm going to quickly make that chart. I didn't see that. Well, I did. So theta, sine, cosine. My major angles are 0, 30, 45, 60, 90. The rule is square root of 1, or square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, 3 over 2, square root of 3, square root of 4 over 2, and backwards. Alright, now what are pi over 3 and pi over 6? Pi over 3 times 180 over pi would be 60 degrees, and then this one is 30 degrees. And I'm taking sine of both. So sine of 30 the sine of 60. Those are the two answers I'm going to get. Okay, here we go. 2 sine, or the square root of 3 minus 2, I'm going to bring that out front, sine 5/2 pi over 3. And I'm going to do the same thing here, except with pi over 6. Okay, let's do some calculations. The square root of the sine of 60 degrees. Okay, so that's going to be root 3 over 2 to the 1/2 power minus 2/5. Let's do this. Sine of 30 degrees, or 60 degrees, and that's to the 5/2 power. Pi over 6 is 1/2 to the 1 power. Notice I wrote this differently. There's no reason, rhyme or reason behind it. 1/2 to the 5/2. Now I'm hoping as you look at this, this doesn't look like it's easily calculable, but I wanted to try it out. If they were nice numbers, you know, manageable numbers, then I would have done it all by hand. So at this point, I'm going to go to the calculator, and I'm going to type in what I see in front of me. 2 times the square root of 3 divided by 2 to the 1/2 power minus 2/5 square root of 3 over 2 to the 5/2 power minus 2 times the square root of 1/2. I wrote that in minus 2/5 times 1/2 to the 5/2 power. Alright, so I'm going to assume that my answer to 4 decimal places is 0.2385, but before I accept that as an answer, I'm going to go back to the very beginning and I'm going to type this in to make sure it does in fact match. So I'm going to take the integral, which is 4 here, from pi over 6 to pi over 3. Remember, when you're squaring or doing whatever with these trig functions, you're going to write it in the parentheses, close the parentheses, then raise it to that power. This one I can do, square root of sine of x. Alright, they match. I feel good about that, so I'm going to box my answer and put that aside. Alright, so that's only part of the lesson for today, sines and cosines. So what do you do with secants and tans? Secants and tans go naturally hand in hand as well. You know, we know that the derivative of tan is secant squared. We know the derivative of secant is secant tan. So what do you do when you're given certain situations? Well, if we have an even number of secants, then what we're going to do is save 2 of them and convert this still even number, right? If you take an even number and you save 2 of them, you still have an even number. You can convert that to tan using a trig identity. If you have an odd number of tans, save a tan and save a secant, because your secants will already be set, and your odd number of tans will include an even number of tans, and those tans can be converted. And then if by chance it's just a tan integral, save 2 of them, change this to its new even number, and then we'll work with it when we see it. But I know that with an even number exponent of tan, I can convert that using a trig identity. Now, what trig identity are we looking at here? We'll go back to the original sine squared plus cosine squared equals 1. If I want secants and tans, then I think about cosine, okay? Cosine would be the decider, I guess, of secants and tans, whatever. If I divide everything by cosine squared, then my next formula says tan plus 1 is equal to secant squared. So as I go through the process, that's the identity that I'm going to use for these problems. Alright, so here's the first one. I have an even exponent for secant. I have an odd exponent for tan. I have an even exponent for secant. I have an odd exponent for tan. Now you'll notice that there's two spaces here because there's two possible answers. So we're going to do it both ways. If I have an even number of secants, I can save two of them. Alright, if I save two of them, then my goal is to have this turn into tan, because tan's derivative is secant squared. So I'm going to convert secant squared to tan squared x plus 1. You can reference that from the previous page. This can now be distributed, giving me the integral of tan to the 5th, plus tan cubed, all receiving secant squared. And I want you to imagine again, I'm not going to write u sub, but do we have the appropriate u sub? If u is tan, and this says u to the 5th du, and this says u cubed du. So my final answer is u to the 6 over 6 plus u to the 4th over 4 plus c. I say final answer, but as I said it, I wasn't writing u, I was writing tan instead. Okay? Same problem, except now look at the tan. Tan is odd, and if we have an odd tan, it said, okay, save one of the secants and one of the tans. Well, this is the derivative of secant. So this secant's fine, it's this tan that we're going to have to change. Tan is equivalent to secant squared minus 1. Distribute. And again, this is the appropriate du for secant, which would be your u. So this just says u to the 5th minus u cubed. U to the 5th becomes u to the 6th over 6 minus u cubed over 3. Sorry, I didn't integrate that at all. U to the 4th over 4 plus c. Well, how can we have this answer above and this answer and it be the same problem? And the reality is, if we went through and actually broke this down using identities, we could get these to match each other. Just understand, as you take your test, you may end up with either of these situations based on your own preference, and that's fine. It's going to take me a while to run through it to make sure that we all have the same answer, but I might be doing the question twice, to figure that out. So know that they are both valid answers. Okay? All right. We're almost done. Moving on. If it's just tan by itself, save two of them. These two tans can be converted using the identity. And that's going to be secant squared minus 1. Okay, so I'm going to now distribute this, and I've got secant squared x tan to the 5th x. No rhyme or reason why I wrote that first. Oops. Okay, so I want you to kind of plan ahead. I now have an even secant squared, which is the derivative of tan. So this is just u to the 5th du. Because it's already to be solved, I'm going to separate this integral into two portions. This one is now tan to the 6th over 6. This one is not complete yet, but it's better off than when we started. So I'm going to do the same thing again. I'm going to save two of them, convert, and I want you to imagine where this is going. This is now u cubed and du, right? If I separated this into two integrals. So, for lack of space, I now have tan to the 6th over 6. I have minus tan to the 4th over 4. And this minus outside the integral with a minus inside, that would have been a double minus. So now I'm adding the integral of tan cubed. This is not ready to be solved yet. However, it is closer than when we started. So just be patient. I'm not writing very slow, so it doesn't seem as though I'm being patient. But save two of them. Convert. Here's what I see. This is going to be secant squared with a tan. Okay, so bear with me. I'm going to do this all in one step, and only because I need to save room. So this is going to be u du. Tan squared over 2, right? U becomes u squared over 2. Then I'm going to distribute this tan. This tan integral has a minus in front of it, and if you remember, we've done this before. Tan becomes sine over cosine. Cosine is your denominator, that would be your u. Tan would then have, or the numerator sine would then have to be negative, which means we have to balance with a negative out front. So now this becomes the natural log of the cosine of x plus c. If you did not do that in your head, that's fine. That is also an available integral that you could have referenced in your book, maybe. Okay? And you would have seen that the integral of tangent would be negative natural log. So in this case, that negative there and the negative here do make a positive. I apologize for no room. And then we will pretty much wrap up here. So we have an even secant. Save two of them. There's your du. That means that tan is going to be our u. That means this has to convert. It's going to be tan squared plus 1. Distribute. I'm not going to write it out, but I want you to see that this is u to the 8th du, and this is u to the 6th du, which means it becomes u to the 9th over 9 plus u to the 7th over 7 plus c. There's a lot of commonalities in these types of integrals. Again, I'm going to go back and look at the one that we skipped and make sure that I figure out how to do that appropriately. Couple things to consider before we move on, and that's special conditions, integrals that involve sine cosine products with different angles. Alright, so in this case, you know, what do? It does say to reference page 529, so I'm going to turn there. And there are formulas that can help you replace them. Okay, so if you have sine of one set and sine of another set, and those two coefficients do not match, then this is equivalent to, and bear with me here, 1/2 times the cosine of m minus n x minus the cosine, and yes, this 1/2 is on the outside of both of these, minus the cosine of m plus n x. So m plus n, this would be m, this would be n, that would be 7 dx. Now, why would that be beneficial? Well, if I stretch this out, I now have 1/2 cosine of negative 3x dx minus the integral of 1/2 cosine of 7x dx. The 1/2s can go out. My u will then be my angle, so if u is negative 3x, then I need a negative 3 and a negative 1/3. I need a 7 and a 1/7. And we know the integral of cosine is sine. Again, I don't have these formulas memorized. I just took this from the page 529. The cosine one is the exact same formula, if I'm looking correctly. Oh, except instead of a minus here, it becomes a plus. But otherwise, it's the same exact formula as before. So you get 1/2 cosine of their difference plus cosine of their sum. Which means we have the integral of 1/2 cosine 2x dx plus the integral of 1/2 cosine 6x dx. You need a 2, need a 1/2 plus this 1/2 that's coming out. You need a 6, balance it with the 1/6 plus the 1/2 that's coming out. And that's not a square. This is going to be 1/4 sine 2x plus 1/12 sine 6x plus c. You don't see a lot of those. So again, that's why I'm referencing the page number and not expecting you to have it memorized. Okay? And that is your lesson for integral or trig integrals.